response diversity and ecological stability. So this is talk number, I've lost track, 8 or so, 6 maybe, in a series of stuff related to these kinds of ideas. We're delighted to have Steve here for a second talk in 1 month. I think he's been hit twice to OIST recently, thanks to Gerald for bringing him here a couple of weeks ago. So yeah, Steve's going to talk to us today about empirical assessments of stability and resilience. And there was rumors of response diversity actually being in this, so we'll see. But yeah, Steve's an adjunct professor of applied maths at UC Santa Cruz in the US. So yeah, Steve, please take it away.
Thanks. So I want to start by saying thanks to Sam for inviting me to come. Thanks to Owen for telling Sam that I exist. And thanks to Jonas for making it possible for me to be here. So I'm going to talk about 2 projects today. One is a model-free approaches to assessing stability for non-equilibrium systems. And then the second one is about thinking about mechanisms maintaining asymmetry in marine metapopulations. But first, I'm going to give a little background on empirical dynamic modeling and why I think this is a useful tool for these guys. So this is a food web from the Gulf of California, and it's got over 100 species and connections between them. I'm not really going to talk about this at all in my talk. The point I'm trying to make is that ecosystems are complex, which I didn't really need to make you all know that, right? But this is just a food web, right? Even though this already looks pretty complicated, it's missing tons of stuff, right? Like non-consumptive interactions, but species interactions and other vital rates are affected by age, size, behavior, and other traits. Those are in turn affected by genes, epigenetics, microbiome. So anytime we go to write down models for ecological dynamics, we're implicitly dividing the world into 2 kinds of state variables. The observed variables, that's X here, those are the things that we care about, the things we have data for. And then Y are the unobserved variables, which is everything else, right? The real dynamics of the system depend on both of those classes of state variables. But very often when we go to write down ecological models, what we do is we try to write down models strictly in terms of the observables, just the things that we care about. Now we know that there are other things exist, and so we usually add some noise to account for that. And then there are conditions under which we can make that rigorous, but you know, most of the time we don't really think about that in ecology. So it's probably worth asking whether we can account for unobserved state variables, and also to account for the fact that maybe we don't know exactly what equations to write down. So the workhorse that we've been using for this for the past decade or so is Takens' theorem of time delay embedding, which I'm totally not going to talk about because I don't want you to end up like this guy. No, I'm not saying maybe this is too much. I'm not saying that you would go on a 3-day drinking binge and wake up in an alley if I told you about Takens' theorem, just that maybe you'd be a bit bored. Okay, so instead I'm going to show you a video, which is more exciting. So, so this is going to be a video of a 3-species system composed of a producer, a grazer, and a predator. The abundance of each species is shown over here, plotted against time. The dynamics look kind of complicated, but when we plot those same dynamics in the phase space, so the coordinates of this are the abundance of each of the species, we see that those complicated time series are actually tracing out a fairly simple shape in the phase space. That's the attractor for the system. Now, the thing in red is a version of the attractor that's constructed using just the abundance of the producer. So instead of the abundance of X and Y and Z, those 3 different species, here the axes are the abundance of the producer now, a step into the future, and 3 steps into the future. The important bit here is that there is a one-to-one connection between these 2 things, and that's what Takens' theorem proves. Now, what can we do with this other than make totally cool videos? Well, let's say that we didn't know the equations for how the system worked, but we did have enough data to make this picture. What can we do with it? Well, let's imagine that what we want to do with it is that we know where we are now, or roughly where we are now, and we'd like to make some prediction about where we're going next. Right? So a very reasonable thing to do is if we knew that we were somewhere in this circle, would be to look at what happened the last few times we passed through that circle, and then use that, or some measure of that, to make a prediction. That's very right. Now, if I did this a bunch of different times, moving the circle around through the state space, and then go a certain amount of time into the future, I'm effectively constructing a discrete time model for the system directly from data. Right? I didn't need to know the equations. I just need to have enough data to make this picture. Now, of course, I can play the same game with the attractor in red, and when I do, I end up with an analogous model in delay coordinates whose dynamics are the same as the dynamics of the full state space, but they're based just on the observed time series. So that's what we get. The equivalence to the full state space is what we get from this one-to-one correspondence between the attractors. Okay, so now Takens' theorem tells us that we can model the next state of the observed variables as a function of past values of the observed variables, but it doesn't tell us what function to use. Like many mathematical things, it proves existence, not what to do. Right, it's kind of useless. But so instead, we have to actually try and infer the delay embedding map from data. There are lots of different ways to go about that. There is no best way. So two very popular ways in ecology are using a nearest neighbor or local linear smoothers. These are popular in part because of the existence of Sukeyhar's RDDM package. But you can also use splines or neural networks. And a lot of the stuff that I'm talking about today is done using Gaussian process regression, which, if you want to try it out, is available through Tanya Rogers' GPDM package. Mostly I'm listing these things just to say there's no best way to go about this. The right way, the ideal tool depends entirely on both what the data look like and what the goal of the analysis is. Right? So some of these work better for estimating the alpha exponents, some work better for prediction. Okay, so here's an example of GPEDM in practice. I'm not going to spend a ton of time on this. It's just an application of the forecasting stuff to time series for Canadian shrimps. These are shrimps in the Gulf of Mexico. There's a survey that's been looking at them for the last 30 plus years. It's nice because they're doing this in 21 different statistical zones. The shrimp are annuals, it's 30 years, 30 generations worth of shrimp, which is great. These are the time series for a couple of zones, but I think mostly I want to draw your attention to this, which is a plot of the predicted catch per unit effort versus the observed. So this is predicted in leave one out, so it's out of sample-ish. The prediction accuracy overall, the R-squared is 0.74, which is not bad for ecological time series. But most importantly, the model that the US government uses to manage this harvested population is a standard parametric population dynamics model. That has a prediction accuracy of 0.21. So we're doing a lot better. And what that means is that using the past abundances of the shrimp are actually telling us a lot more about the shrimp dynamics than just conditioning on the current. Okay, so of course this isn't a conference on forecasting, so what else can we do with EDM? Lots, and I really, this is mostly for advertising purposes. I'm just going to talk about, for a second, about this one bit here. Is we have time series, multiple time series from a given system. We can use EDM to identify interaction networks, and then to estimate context-dependent interaction strengths. And that's, seems like it might be a useful thing in the context of Fred's talk and then some of the stuff we'll do in the workshop next week. But I'm not going to talk about that anymore. What I want to focus on is estimating context-dependent stability using EDM. So a bunch of the other talks in this group have talked about how you can measure stability, local stability. So I'm not going to talk too much about that now. But let's say we have some discrete time dynamical system, and the current state is xt, and we have some small perturbation, like we're going to change it by just a tiny little bit. The dynamics of that perturbation then are given by the Jacobian matrix, which is the matrix of partial derivatives evaluated at xt. So other folks have talked about using that to measure local stability of a fixed point, right? But we can measure stability for any point in the state space using this. Right? And if we, instead of wanting to think about a specific point, we wanted to think about a trajectory, then what we could do is say, okay, evaluate the Jacobian here, and then go a step into the future and evaluate the Jacobian here, go a step into the future, evaluate the Jacobian, and then the product of those gives us the stability of that trajectory chunk. So that can be really useful. That's the math. I wanted to show this in a more visual way. So if we want the stability of this point, we want to characterize that. We can think about looking in a small neighborhood of that point and what happens to trajectories as they pass through that small neighborhood. If as they pass through that small neighborhood, they get closer together, then that neighborhood is stable. Okay. If instead they get farther apart, then it's unstable. We can measure the sort of how much that distribution of future points grows or shrinks by looking at the lengths of the axes of that ellipse. Right, so this is just like using eigenvalues. Right, so we can calculate from those axis lengths. If we take the log of those and divide by how long we've been looking at the dynamics, we get a rate which measures the rate of shrinking or growing of the axes. These are the local Lyapunov exponents. If we take the time over which we're looking at this over a long period, say over the full length of the time series, or really the definition is infinity, not practical. But if we take it over the full length of the time series, then we're characterizing the stability in the long run, and a positive exponent is typically taken as an indicator that the dynamics are chaotic. Okay, so that's the setup. Here I want to show you an example of this working for a simulated system where I know what the right answer is. And I'm using a discrete time predator-prey system. This is the multi-species record that Tad and Mike were showing in their talks. The dots are the simulated data, and the blue line is the step ahead prediction for a fitted EDM model. So the model does pretty well at reconstructing those dynamics. But now because it's the simulation, so I know what the right answer is, I can calculate the Jacobian for each of those blue dots, right? And then ask what the dominant exponent is for that. When I do that, this is what I get, where it's very clear that the stability above the black line is unstable, below is stable. So clearly the system is oscillating back and forth through intervals of instability and stability, right? In fact, if we take this instead and plot it as a function of the current state of the system and the next state. So this axis is the prey abundance and the prey abundance next time. Right? And the color indicates stability. So red dots are unstable, the blue dots are stable. There's very clear state dependence in stability. Right? This is a region where things are unstable. This is a region where they're stable. So, but that's the right answer. That's what I get directly from the simulation model. How am I going to do this with EDM? Well, I'm going to take my fitted EDM model and then do all the rest of the same stuff. Right? I'll calculate the Jacobian from the delay embedding map, write the exponents from there. And when I do, this is the picture that we get. It's not exactly the same, but it does do a pretty good job of characterizing the state dependence of stability for this system. Okay, so this is simulated data, right? So everything works better for simulated data. So here's some real data. This is an application to a marine copepod. These are the abundance time series. But we calculate the long run stability of this weakly chaotic. So the Lyapunov exponent, or the long run stability is weakly unstable. But we can also calculate the local stability, which I think is more interesting here. And just like in the simulated data, the local stability here shows periods of instability and periods of stability. So and it looks remarkably like what we saw in the simulated series, right? So of course, this is just one data set, right? So a very reasonable question is how widespread is this sort of time varying local stability? So to get at that question, we assembled a database of 154 species level time series from 17 different lakes and then 4 marine sites. And when I say we, I mean time. Time and Rogers did all of the legwork here. I can't really take any credit. Okay, so using these 154 time series, we calculated the EDM-based Jacobians to look at local stability, and then the long run, the Lyapunov exponent to look at whether or not the dynamics are chaotic. We then assess the prevalence of seasonal fluctuations in local stability, and whether or not that's tied to whether a time series is classified as chaotic or not. And then we asked about how these results are affected by the level of data aggregation. If we're looking at individual species level time series aggregated to functional groups, and then to trophic levels, which trophic level here is not really true. Phytoplankton and zooplankton. Right? And if you're mentioning this because people who study zooplankton know some of the others. Or so I'm told. Okay, so here's an example of how this turns out for one of the other species. This is the abundance on the left. In the middle is the local stability, and just like in the previous case, we see that there's a very obvious annual cycle to local stability. In fact, if we take the power spectrum from there's a very clear peak at 1 year, or it would be clear if this axis wasn't in frequency, the period. But that is a 1 year, it's 12 months. And then this is 6 months. The secondary peak is 6 months. Okay, so and overall, this time series classifies as weakly chaotic. Here's another example. This one has also sort of seasonal fluctuations in stability, but it classifies as basically stable, or basically a limit cycle. And then here's one where there's no instances where we have instability, right? And of course, if it's never unstable, then that can't. Okay, so how often do these things occur across all 154 time series? Tanya made this figure to summarize that, and let me try and walk you through it, because I don't think these make that much sense. But the horizontal axis here is telling us the frequency with which we see things being chaotic and having fluctuating stability. This is where things are not chaotic, but the stability does oscillate between positive and negative values. And then this is the frequency with which things are just always stable. So about a quarter of the time, things are stable. 3/4 of the time, they're not. And then the vertical axis here is within each of these categories, how often do things exhibit sort of seasonal fluctuations in stability. So when things classify as chaotic, about I don't know, 2/3, 3/4 of the time, we have this annual cycle of stability, and it's less than these other categories. It would have been better if we had, but sorry. Okay, so I did want to talk a little bit more about the connection between variability and stability. So a lot of the time when you see people looking at time series and talking about stability, what they've measured is the coefficient of variation. I think it's a little weird in that if you have a cycle, right, and the mean, they have the same amplitude, but the mean is high, that's got a lower CV than the same cycle down here. Right? If you leave the mean here, but increase the amplitude, it's still a cycle, but now it has a high CV. So it seemed to me like you could make that work in lots of different ways, right? And when we look at the species level time series, there's only a weak relationship between the coefficient of variation and the Lyapunov exponent that we get. But interestingly, once we've aggregated across functional groups or trophic levels, now the correlation between variability and stability is a lot higher. Still not stunning, but it's a lot higher. And that suggests that something interesting is happening when we're aggregating. Thinking a little bit more about aggregating. So these are distributions of CV, Lyapunov exponent, and prediction accuracy for things aggregated. These are the individual species level results. Then the blue is aggregated to functional groups, and red is for trophic levels. And then across these, we see that aggregating reduces variability. It dampens instability. So the red curve is shifted that way. And it increases predictability, right? And I don't know, I mean, I hadn't really thought about this before this workshop, but is this an indication that we have response diversity? I don't know, maybe. certainly seems consistent with what we're expecting in terms of effective response to this. I have one more slide on the stability stuff, which was entirely for Karen Abbott's benefit, and she's not here, so I don't know. I'll do it anyway. Okay, so Karen gave this really cool talk about using potentials to characterize sort of a global picture of stability, and criticizing the local measures of stability. And while what I was doing is it's not as local as asking about the stability of a fixed point, it's still local in that we're thinking about stability along a trajectory. So I do think that this potential stuff is nice, and I also really like Wile E. Coyote. So I thought, okay, well, after I saw Karen's talk, well, can we reconstruct a potential from time series using EDM? So I simulated some data from a classical system with a double well potential. The potential is shown here. The stochastic differential equation is here. The point one is just to make this asymmetric. Here's the time series that comes out. And so it spends a little bit more time in the lower well than it does in the higher well. Okay, so how are we going to reconstruct a potential with EDM? Well, so the first thing to do was to try and model the first differences. So the blue dots are first differences plotted as a function of the current state. The red line is the fitted GP EDM model to that. And then to get to the potential, well, I just use the definition, which is the potential is going to be an integral of this, the function of x. So we integrate over x, and we get this. The red line is the posterior mean estimate of the potential with its associated confidence band, and the black line is the right answer. So the black line there is the same as the black line there. So I don't know. I thought that looked pretty promising. I didn't try very hard. I just did this last week. I think there's lots of more stuff we might do with this. I don't know. Okay, done. So moving on to mechanisms of asynchrony in marine metapopulations. So why asynchrony? Well, like in Sam's talk at the very beginning, we have this notion that asynchrony implies greater resilience, and because there's plenty of theoretical reasons to think that increased synchrony leads to increased chances of global extinction. Although I'm pretty sure that nothing's gone extinct because it was synchronized. So much like once it's extinct, it's zero everywhere. So okay, so the theoretical foundations for synchrony in ecology are actually pretty well established. We've been at this for a couple of decades now, like almost 50 years, maybe more. So the conditions required to generate synchrony are that we either have dispersal among populations, or we have some spatially correlated driver, whether that's an environmental driver or some other species that's widely distributed. Either of those works. Classical theory, theory from the 1990s by Landy and Cedar, shows that the spatial scale of population synchrony should be at least as great as the spatial scale of environmental synchrony. The reason for that is that the coupling by dispersal sort of smooths out the kernel for spatial environmental synchrony. Okay, so so I got into this stuff actually because when Tanya Rogers was a PhD student, she was working on metapopulation ecology of blue crabs, and had assembled this really neat data set going with 17 different sites going from Florida up to Massachusetts on the east coast of the US. And this is on blue crabs, which live in coastal estuaries, and as a consequence, they're strongly affected by temperature and rainfall. And we know a whole lot about these crabs, because they're commercially really important. One of the things that we know is that their larvae have pelagic dispersal, so that they have these cute little larval stages that get pushed around all over by currents. And we know that the known environmental drivers are actually relatively spatially correlated. So putting those things together, the classical theory says that crabs should be pretty highly synchronized. But when we actually look at the data that Tanya found there, they are not synchronized. So at first, what is going on? In fact, if you look at the correlations are mostly less than 0.2. So really not synchronized. So, the first most obvious hypothesis for why they're not synchronized is that the data are just worthless, right? The data are junk. But I don't think that's the case because the series are within each individual time series, they're actually fairly predictable. The average of prediction accuracy, at least 50%. So it's not that the data are junk and it's all observation noise. Maybe it's because the environmental drivers are correlated on a shorter time scale than it looked from that figure. No. So the crab abundance decorrelates within about 500 kilometers, right? So the spatial scale of synchrony in the crabs is less than 500 kilometers. The known environmental drivers are still positively correlated for 1,000 kilometers or more. So at this point, if you're a die-hard true believer in the classical theory, what you say is, well, you just didn't find the right environmental driver. But that is not a falsifiable hypothesis, right? I mean, how many drivers do you have to find before you're willing to accept that it just doesn't work? So anyway, so I don't think that's it. At least we know over the known environmental drivers, they're correlated over much longer distance. So maybe it's differences in local dynamics, which in the context of this group, I would call response diversity, right? But how are we going to measure response diversity if we don't have a model, right? So if I had a model for how the dynamics work, what would I do? I would say, well, I'll fit that model to the dynamics in location 1 and in location 2, and then I ask how the parameters differ. And that's a very reasonable way to go about that. But I don't want to have a model. I want to do this with EDF. So how am I going to do it? Well, the idea is to use a hierarchical approach to EDF. So we're going to say that the dynamics in each location in site I depend not just on past population sizes, but also on the past values of the environmental drivers, and that we can decompose this function, the delay embedding map, into a common mean function and then some site-specific deviation from that. So the common mean function is over here in blue. The site-specific dynamics are in red, and we can think about the deviations between them as some other function, right? So if I set it up this way, then we're squarely in the framework of a Bayesian hierarchical model, which allows us to define a single parameter called the dynamic correlation, which measures similarity in the delay embedding maps between two locations. So it's not measuring similarity in dynamics through time, it's asking how similar these shapes are. So why do we need that? I'm going to spend one slide to emphasize why we need this. So let's say we have the same map, two locations that have exactly the same model, right? And we force them with independent noise. The time series that we generate look like this. And then if we plot population 1, the abundance of population 1 against the abundance of population 2, they're if instead I force them with correlated noise, then I end up with correlated time series, right, for population 1 and 2. And these are the sort of intuitive cases that we all kind of think about when we're thinking about this. But that's not the only things that can happen. If instead I have both populations still have the same dynamics, same model, right? And I'm going to force them with correlated noise, but now the dynamics are unstable, right? I force them with exactly the same correlated noise that I used over here, and I end up with uncorrelated abundances, right? Because the dynamics are unstable, right? Now, conversely, I can take two different maps, right? Two different models for each population, force them with correlated noise, and wind up with nearly exactly the same abundances. So, to summarize this, the same model can generate correlated or uncorrelated time series depending on noise and instability. And different models can actually generate strongly correlated time series, right? But there's another way. Temporal correlation does not mean that the underlying dynamics are the same, and a lack of correlation does not mean that they're different. I'm beating this dead horse because I had to go 3 rounds with a reviewer on this paper to get this across, and so I'm not bitter. I just want to make sure that there's no confusion. All right. So when we apply our dynamic correlation to the crab time series, this is what we do. This is the correlation thing that I showed you before with the correlations through time, and this is the similarity in the delay embedding maps. So most of these values are up above 0.5. Almost all of them are above 0.5, and there's clear spatial structure. So things are much similar, closer, and then less similar farther away. And that's, intuitively very reasonable. But in fact, they're so similar across the coast that it turns out that the differences in local dynamics are not sufficient to explain the lack of correlation or the lack of synchrony in the crab population. And that gets us to our final hypothesis, which is that maybe it's environmental gradients that are important here. Now, all the classical theory says that we have a synchronous environmental driver, right? And we do. We know that the temperature is fluctuating up and down from one year to the next in a way that's pretty synchronized. But we also know that it's hot in the south and colder in the north, right? And that probably matters, has different effects on the dynamics, right? So, and it's particularly relevant in the crabs, where we know from our fitted EDM model, so this is the thermal performance curve that we infer from the population time series. So the vertical axis here is temperature, either in January or August. The horizontal axis is population size, and the color indicates the expected abundance of crabs next year. Right? And so this is indicating that there's a unimodal thermal performance curve, but the peak and how steep it is depends on population size. And here, where the peak is depends on population size. So if I drive a latitudinal gradient temperature through this, it's going to have different effects in different places, right? Okay, so to ask whether this is actually what's going on and controlling synchrony in the crab populations, we'll do a simulation using the EDM model to generate a predicted level of synchrony. So we'll simulate under the original environmental setup. So this is where there's differences between locations of the mean temperature, and each location has its own original sequence of interannual fluctuations. Our first alternative is to say that we're going to leave the differences in mean intact, but make the interannual fluctuations perfectly correlated. Our next alternative is to leave the interannual fluctuations intact, but take away the difference in means. All right, and then the last is to make the environment exactly the same for all locations. All right. So when we do that, here's what we get in terms of our predicted correlation. So the green and the orange lines are these two cases where there are still differences in the mean temperature. Right? And those drop to zero at around 500 kilometers, just like it does in the real data. In contrast, once we've taken away the difference in average temperature, we get synchrony, predicted synchrony in the crabs out to all the way to the end. And so I think that this is a very plausible explanation for what's going on, right? If we have a shift towards warmer temperature and that's driven through a unimodal thermal performance curve, then where it's already hot, things get worse. Where it's cold, things get better. So that's enough to cause things to desynchronize. Maybe it's environmental gradients filtered through nonlinear population responses that desynchronizes the crabs. So that's the hypothesis we're left with. Now, a couple of obvious questions come up. Right? The first is, are the crabs just weird? Right? Are they uniquely asynchronous amongst marine metapopulations? So we did a little mini review looking at, and again, this is fine. Looking at where we looked at 67 species of marine ectotherms, ranging from copepods to fish, where it was possible to get an estimate of the spatial scale of population synchrony and a spatial scale of a known environmental. And when we do that, this is what we get. So the horizontal axis here is the relative scale, the scale of the population synchrony versus the driver synchrony. The theoretical prediction, remember, is that this should be bigger than 1. And in fact, most of the time it's down here around 10%. So this level of asynchrony, the spatial scale of synchrony in living things is much less typically than the spatial scale of synchrony in known environmental data. Is not unique to crabs. It actually seems to be quite common, which is sort of a surprise since there's tons of papers on synchrony and where people measure the correlation between things, but as far as I know, we never found anybody who's compared it to the synchrony in the environment and said, hey, the theory doesn't work, right? Okay, so another obvious question is, well, if synchrony is inhibited by latitudinal gradients filtered through nonlinear performance curves, then then places with flatter gradients should have greater synchrony, right? Okay, so to get at that question, postdoc Vadim and Teresa have assembled a database of 36 species, 12 of which are in sort of taxonomically matched pairs so that we can account for life history differences. And they come from the US East Coast and the West Coast. So the reason to focus on the East Coast versus West Coast of the US is because the latitudinal gradient in temperature and other drivers is a lot steeper on the East Coast than it is on the West Coast. So immediately we have a hypothesis that, at least in our pairs of taxonomically similar species, we should see more synchrony on the West Coast, right? And that's in fact what we found by a lot. So for all of the pairs, taxonomically paired species, there's more synchrony on the West Coast than there is on the East Coast, except for herons. And these really aren't actually the same species, but so as far as I was concerned, done. Hypothesis tested. I was very happy with how this turned out. But Vadim wanted to keep going. And so he wanted to ask about what the likely impact of climate change is going to be on synchrony. So we all know that climate change is increasing the magnitude and frequency of extreme events. Somewhat less well known is that climate change is decreasing the steepness of latitudinal gradients, and that's because it's warming faster at high latitudes than at low latitudes. So that's flattening gradients by bringing up. Okay, so to get at what will happen to synchrony in all 36 species that he was looking at, he did basically the same thing that Tanya had done with the crabs, where we simulate future environments to ask what happens to predicted synchrony. So, so he fit our hierarchical EDM model to include temperature, upwelling, climate indices, zooplankton, and productivity. And then he allowed for among-site variation in a way that's a little more general than what Tanya did, where he split it up so that there's the possibility of among-site variation in the response to past abundances, and then a separate hierarchy for response to the environmental drivers. So we're hoping to be able to separately estimate demographic response diversity or response to past abundances from environmental response diversity. And then we simulate future environments and ask what happens to predicted synchrony. Okay, so before I show you how the simulation stuff turns out, the vertical axis here is the contribution to prediction accuracy for each of these different cases. So the things to take from this are that there's almost no evidence on either coast across all those species of demographic response diversity. Sort of response to density dependence is very similar across all species, or within species across location. Environmental response diversity, there seems to be a lot more support for that, and more strongly on the West Coast than the East Coast. And the importance of environmental gradients is there as well, but much more on the East Coast than on the West Coast, which makes sense considering that the West Coast gradient is a lot shallower. All right. So what happens with the future of synchrony? So Vadim, to simulate the increased frequency of extreme events, Vadim took the purple distribution, which is the sort of this current historical environmental distribution, and then tacked on some crazy extreme values on either end, which I might put this way, but you know, it's definitely more extreme. So you know, think of it as an upper bound on what might happen. When he does this, this is what we get. So the vertical axis is the change in synchrony. The dots are for each species, color coded by West Coast and East Coast. The horizontal axis here is the strength of the environmental gradient. Now, there's only East Coast and West Coast. There should only be two values there, right? But he did this thing which is kind of clever, since he's got a bunch of different environmental drivers, and each species responds in a different degree to each environmental driver. He's calculated sort of a weighted mean environmental gradient here. So where the weighting is from how sensitive the species is to that environmental gradient. Which I don't know, I hadn't thought of that one. All right, so before I show you this is the increase in synchrony, which is not much. So we go from roughly 20% increases. But if we throw in the weakening of latitudinal gradients, this is what we get. So especially in places where the things were asynchronous because of strong environmental gradients, taking away the gradient is predicting a much bigger increase in synchrony and a concomitant decrease in resilience. So we're measuring that in terms of the lower decile of region-wide population abundance, right? So we're taking what's the worst case, the smallest 10% of region-wide total abundances. And so we see that that goes down fairly sharply, especially for things that have strong environmental. So to sort of summarize, I started out by talking about stability in non-equilibrium systems, how we can measure that using EDM directly from time series, and showed some evidence that it's generally concepts that kind of varies a lot, where it commonly varies and often has an annual cycle. Then I talked about asynchrony in marine metapopulations and how this seems to result from a combination of environmental gradients and environmental response diversity. And we have this prediction that as climate change weakens gradients, synchrony is expected to increase, and that effect is likely to be stronger than the effect of increased extreme events. And last, I wanted to close by saying that empirical dynamic modeling, I really like it for this kind of thing because it lets us address questions in complex systems with relatively minimal assumptions about how the system works, which, when we're thinking about field data for any particular species, well, that species is, ineluctably meshed in a network that has lots of other moving parts. And so I like EDM for this kind of. Lots of people have contributed to this over the last decade. And with that, we'll take any questions.
Okay, thanks, Steve. Lots of really cool stuff in there to think about. We've got about 5 minutes for questions. Anyone wants to kick us off?
I have a quick, really silly question.
Go on. I love a silly question.
Great talk. So early on, you showed time series and we're talking about local stability. And you showed the abundance time series and the local stability time series. When abundance went up, local stability went down. And the opposite.
Yep.
Why?
Oh, so when we were looking from one year to the next, right? During the winter, when things are converging, they're all converging to low values, and so they're all going closer together, right? In the spring, right, when they're growing, everything's going to, but from one year to the next, what value they go to is not the same, right? Okay. And so this picture of instability in the, in terms of peak abundance is actually consistent with the observation that we're very good at predicting that there will be a spring bloom, but not so good about what species will dominate. So that's where we have predictability in terms of like aggregated across lots of species. But plankton in general will get higher in the spring. More nutrients, more light, less stratification. On the other hand, telling which species is going to dominate is a lot harder, and that's consistent with this.
Other questions? Mike?
Thanks, Steve. I really enjoyed that. I have lots of questions, but I'll try and limit myself to most generally interesting. How data hungry is EDM? So I was thinking about this with the simulated example you give for Karen, right? And
with an absurd 500 number, 500 points. Yeah.
So to find those two wells, it looks like with the confidence bands around the shallower well, you can't really be very confident that that's actually a well. It might be a kind of, it could be anything from a slight flat incline or flat incline. That doesn't make sense. But so how much data do we need to be able to make reliable ecological inference?
About potential, that's the only simulation I've ever done on that. And so I thought of that as proof of concept, right? So when I do the proof of concept things, I take very long time series just to make sure that it's not working because I didn't even know. Right? So the next step obviously would be to sort of work backwards. How little data can I get? And I think for the potential thing, maybe that's not, maybe you just need too much. But it might also be that those dynamics are really stochastic, right? A lot of the other time series just don't have anywhere near that amount of stochasticity. Well, when you fit it with a low deep current measure, it looks like a lot of nodes, but you end up with a lot less prediction error, like the 20% versus 75% prediction accuracy for the shrimp case. Right? So the fisheries managers all say the shrimp dynamics are totally noisy, completely dominated by the environment. And then we come through with the EDM model and predict 75% of the variability just using past values of shrimp. So with regard to the Karen's thing and the potential, I mean, I had to really get a ton of noise to make it bounce to the other well, right? So I don't know how feasible that project is at all. It's kind of hoping.
That's a kind of, sorry, it'd just be a second, kind of interesting question to pose with that system. It's like how much data would you need to be able to really apply this?
I might be able to answer that. Yeah. So because I'm a sort of practitioner of this general.
Sorry, we must use the microphone.
Yeah. So I'm a practitioner of this general EDM business. And it really depends. You don't have a hard answer for this thing because it depends on the particular structure. For example, if you have something that's fairly regular and fairly clean, you can get away as few as 50 time points, and the dimensionality is relatively low. However, if you have something that is like the dimensionality is higher, then you run out of data because you basically is under constrained, and then you don't have a good picture of the whole thing. So it's like there's no absolute answer because it depends on various things. It depends on the complexity of your system. So the intrinsic dimensionality of the system limits how much data you need. It also depends on, like, for example, something similar to what Steve has done is like we actually did with mice activity in a cage, and we can actually see like 3 states of the mice with something around 100 data points. So that's sufficient to find this thing, but it really depends. You don't have a hard answer, but like we have done things as few as 50, and you're typically comfortable with a couple hundred, I would say. And you have to have a number of events.
Simulated data, if I simulate data for a logistic map, I can do pretty well with 15 data. But all I'm trying to do is reconstruct it for Avalon. So the key ingredient there is the recurrence time. So the way all of this stuff works is you're using the similarity in what happens to the next state, given that you have a neighborhood of points. And so that means the system has to come back. So you need several recurrences to make it.
Yeah, cool. I think what you both just said is instructive from an ecologist's perspective, because we were discussing some of the data sets that Tad's used and I've used. They have a median, so population time series from the biggest database that we've got of these, which starts at 5,000 time series, and then you filter them out, getting rid of all the low quality stuff, and you're left with a couple of hundred, and the median length of time series is about 25 data points.
Yeah, when we did this filtering of the global population dynamics database, we set a minimum time series length of 30 points. We end up with 170. So yeah, you throw away a lot of those time series, but the things you're throwing away are 6 to 10 points long. So are we throwing something away? No. Yeah. Those are valuable for asking different questions. No. Yeah.
But there are also tricks to take those little bits and pieces and then assemble to things that, for example, equivalent. Let's say if you have some ecologically equivalent species that sort of, for a particular predator, for example, they're redundant. They're all their prey. you could actually put them together in something we call dewdrop regression, where you can actually put them all together and just extend time series when
That's
from
actually what we did with that hierarchical. That was the first reason to develop a hierarchical EDM, was to be able to stitch together time series that are short. You need them enough to synchronize. You need the dynamics to be measurably similar.
Cool. Thank you. Well, in the interest of time, I guess we'll maybe stop there for now, but there's plenty of time this afternoon for discussions, so please talk to either of our speakers afterwards. Thank you very much, Steve.
Thanks for listening.
Yeah. So next week from Monday, well, no, Monday we have an excursion. From Tuesday, we start our workshop on response, diversity, and stability, which is closed to those who've registered, but there will be 3 open talks, still 3 more in this series, from Laura D, Ceres Barros, and Rachel Winfrey next week. That's Tuesday, Wednesday, and Thursday. Thank you.